We're pleased you have joined us for today's discussion on the state of obsolescence and the impact on manufacturing. I'm Betsy Brennan, today's moderator, and I'd like to cover a couple of housekeeping notes before we begin. All attendee phones have been muted for clear audience listening. We encourage you to submit any questions that arise during the presentation. You may type your questions in the questions section at the bottom of your viewer panel. At the end of the presentation, we will be addressing all questions submitted during the webinar. Now let's get started. I'm going to tell you a little bit about Polytron, then we'll move on to discuss the state of aging automation, identifying risk, obsolescence migration, and end with questions from the audience. Who is Polytron? Polytron is a CSIA certified systems integration and engineering consultancy founded in 1983. We are focused on full system integration in the areas of automation and controls, MES and manufacturing intelligence, packaging, emulation, turnkey project management, and technology transfer and training. All of our project engineers are PMP certified, and our project leads and senior engineers are licensed PEs. We strategically partner with leading technology suppliers in the manufacturing industry, which enables us to present the best combination of innovative technology and solutions for our clients. Today's presenters are Richard Phillips and Tony Parker. Both speakers are project managers and product managers and have been with Polytron for over 20 years. And now I will turn the presentation over to Richard Phillips. Richard?
Good afternoon, everyone. Today we'll be discussing the state of aging automation assets within the manufacturing environment and its impact as more and more of these assets are becoming obsolete. Automation hardware and software becomes obsolete when it is no longer supported by the vendor who developed and sold it. Most hardware and software vendors can only provide spare parts, technical support, patches, etc. during a given product life cycle before they need to focus their attention on newer technologies in order to remain competitive for new sales. We'll also discuss the risks associated with these aging assets, options for mitigating these risks, our approach for executing automation migration projects, typical scenarios, and finally, opportunities that come with migrating obsolete automation to more modern technology. Some aging automation statistics. Industry Week reported that almost 75% of the U.S. plants are more than 20 years old. That's not surprising given that modern manufacturing automation with computer-based control systems became commonplace about 20 to 30 years ago. Many of these manufacturers continue to use their original automation assets to produce their products. In a 2010 study of process automation users, the ARC advisory group reported that 91% of manufacturers use automation systems beyond the manufacturer's obsolescence date, and 36% of these manufacturers do not have a life cycle plan. Also, according to the ARC advisory group, there is currently more than $65 billion worth of legacy automation assets reaching the end of their life cycle. This includes items you're most familiar with: programmable logic controllers, PLCs, variable frequency drives, VFDs, distributed control systems, human-machine interfaces, network hardware and software, etc. With such a large investment at stake, careful attention should be paid to developing an effective migration strategy that helps ensure the upcoming investment will best meet the manufacturer's present and future needs. In addition, the ARC research indicates that a total cost of ownership for an automation system is about 4.5 times the initial investment based on a 20-year usable lifespan. Further impacting the obsolescence issue is this aging workforce of plant support technicians. As these folks retire, they take with them knowledge related to the legacy systems. Plant Services Magazine estimates that only 3 to 7 new employees will be hired to replace every 10 retiring maintenance workers. This, coupled with estimates that 42% of plant knowledge resides with employees, with only 26% of that knowledge being documented, and only 20% maintained in electronic format, creates an additional risk associated with legacy systems. Therefore, the timing of when this tribal knowledge retires should also be considered. The asset failure life cycle, commonly referred to as the bathtub curve, can be seen in the figure that's on the screen. It's widely used in reliability engineering. The name's derived from the cross-sectional shape of the bathtub. The graphic depicts the measurement of the rate of failure over 15 to 40 years. The bathtub curve is generated by mapping the rate of early failures when introduced, the rate of the random failures with constant failure rate during its useful life cycle, and finally, the rate of wear-out failures as the product exceeds its design lifetime. In less technical terms, what this means is in early life of a product, the failure rate is high but rapidly decreases as defective products are identified and discarded. And early sources of potential failure, such as the handling of the product, installation error, and so forth, are discovered. In the midlife of the product, it reaches steady state. The failure rate is low and constant. Late in the product life cycle, the failure rate increases as age and wear take their toll on the product. Manufacturing companies are in constant struggle to get the most out of their current asset base, given the eventual aging of the asset. It is a balance of these two pressures to maximize asset utilization without sacrificing safety, processes, and the quality of their manufactured goods. So what are the plant conditions that impact the failure rate? The expected automation asset life cycle is further eroded by plant conditions outside of the optimal operating environment. The extent to which one or more of these conditions exist will have a direct effect on the rate of the failure. This may shorten the manufacturer's stated life cycle further for assets exposed to adverse conditions, such as those listed here: excessive moisture, high temperatures, vibration, corrosive agents, and excessive loading, and others. So what are the risks associated with assets reaching their obsolescence state? So the major risk is unplanned downtime. As we saw in the bathtub curve, wear-out failures increase significantly as the asset reaches its end of life. This is no different than the parts in your car, or washer, or oven, etc. There are always outliers, but most of these fail within a given window of time. For manufacturing environment, a part failure typically means unplanned downtime, which has a significant impact to production in terms of cost, ability to fulfill orders, etc. Estimated costs for unplanned downtime can reach the $1 million range easily for every hour of downtime for certain manufacturers. Another risk is security exposure. With the retirement of Windows XP earlier this year, the security exposure for many manufacturers is expected to rise as they delay transitioning to more modern operating systems that provide a greater protection from malicious software intended to disrupt or gain access to information. The risk is mostly due to Microsoft no longer issuing new security patches to protect from the latest malware attacks. This is not a small issue, as 70% of Microsoft's technical updates deal with security patches. Another risk is compliance issues. Meeting the latest regulatory standards while operating the legacy hardware and software becomes increasingly challenging, since these platforms do not have the out-of-box functionality required to meet the latest requirements. Fines, penalties, or disruptions resulting from environmental, FDA, or OSHA infractions due to improper reporting, operating outside of specified limits, unsafe machines, and so on, seem to be on the increase given the latest regulations. Timely access to information. Legacy systems are typically not networked, or are networked using outdated communications protocols. Many times this creates intermittent communication issues that are difficult to troubleshoot. These islands of automation also restrict timely access to critical data needed to effectively troubleshoot, control, and integrate manufacturing systems. And finally, just general production limitations. Legacy hardware and software restrict the manufacturer's agility in meeting their supply chain demands. due to greater difficulties with controlling scheduling, controlling production, controlling line downtime when it occurs, quality control, maintenance, and so forth. So the chart shown up on your screen now identifies a pictorial of where we consider the danger zone to be. So we've identified some of the symptoms and approaches that might help you identify your current obsolescence risk level. So the symptoms shown on the left are basically the symptoms we covered previously. In addition to those, how many assets you have that are obsolete, how long these assets have been obsolete. Both of those increase the risk of the obsolete assets affecting your production. In terms of approaches, these are things that we see manufacturers do to help mitigate those risks on a temporary level. So in addition to the identified risk, these are the steps. So reactively pricing obsolete parts as they fail, shopping eBay and stockpiling parts, shopping on eBay for spare parts or stockpiling spare parts borders on the danger zone. eBay has become an industrial parts locator for many businesses. This approach indicates that your operation is basically no longer sustainable in its current state as the parts on eBay become no longer available. Sharing spare parts between plants, that's a strategy that we've seen deployed as well. As certain plants upgrade their systems, they may send those obsolete assets to other plants who have not gone through the migration process yet, so that they have additional spare parts on the shelf. The lack of a life cycle plan, overall just coming up with a game plan as to what's going to be done to either in a phased approach or in a rip and replace approach, which we'll cover later, how to go about replacing the obsolete assets. And then a delayed phase migration, that is when you're migrating in phases that may get drawn out for budgetary or other purposes. You're slowly mitigating the risk, but you still have the risk for the assets that have not been migrated yet. So what are the options for developing an effective migration strategy for these obsolete assets? Our approach for defining and implementing migration projects consists of the following steps. First one is a system assessment. Initial step is to survey the existing automation assets, collect key information on each asset in order to develop an accurate picture of the overall scope. A risk assessment matrix is then developed to identify and prioritize the perceived risk associated with each asset. Once the risk assessment matrix has been completed, the next step is to develop the desired future state of automation that will meet the company's or individual plant's short-term and long-term needs. This can be developed at the individual plant level or across multiple plants. So what is the desired future state of automation? Future state should include the infrastructure and the latest technology selected upon which applications will be developed. This means that the migration plan may not necessarily consist of a one-to-one asset migration. So for example, instead of migrating a Rockwell legacy panel view to the latest panel view plus, you may want to consider implementing a thin client-based server-client architecture. The intent is to develop the automation architecture and platform that takes advantage of the latest technologies in order to best meet the plant's current and future needs. Once the desired future state is identified, then it becomes easier to lay out a roadmap for how to get there. In terms of the actual migration plan, there are several options that we've run across for implementing a migration strategy. Some of the most common ones described here. Phased approach, I mentioned earlier, identifies what are the high-risk assets and targets those assets to be replaced, all or one at a time over a specified period of time. This approach is aimed at quickly reducing the highest risk assets first. The risk in this approach is that the other obsolete assets may continue to impact production and increasing efficiency based on the declining expected life of the asset. The rip and replace strategy, it's more of a wholesale or bulldozer approach, if you will. It's the most efficient approach in terms of rapidly eliminating the long-term risk of the obsolete assets. It's the most intrusive approach for operations because it's going to require a greater amount of downtime and more than likely a longer startup curve, depending on what is being replaced. but it has the advantage of getting everything done at once without having to operate two different systems, a legacy system and then a new system. The multi-plant rolling upgrade is a combination of these. This approach is often seen as the migration plan for a manufacturer maybe that has multiple plants. They're all about same age and require upgrades during the same period of time. Migration plan is created for each plant, and the risk assessment for the obsolete assets determines the order of the migration across the multiple plants. So obviously the highest risk plant typically receives attention first. The upgrades go through that plant and then followed by subsequent plants and so forth. As you can see, there's many variations of the above options that are also possible based on the manufacturer's specific needs. So once we develop the migration plan, we use a proven project execution approach, which should be followed to help ensure success. This includes various project phases indicated along with ultimately validating the system to make sure it functions as expected, and then associated training for any new technologies that were deployed. Depending on the size of the project, a front-end definition plan can be developed that describes the scope, risk mitigation, schedule, cost, etc. for implementation. Definition plan we typically see as a requirement for some manufacturers who will need this level of project information to get funding, to request funding. Next, Tony Parker is going to discuss the most common obsolescence scenarios that we run across, along with our specific approach, and present typical solutions for the various scenarios identified. Tony?
Thanks, Richard. The 6 most common scenarios that we encounter related to obsolete automation assets are listed on the screen. This represents the bulk of what most manufacturing plants have to address as they approach the asset's end of life cycle. The good news is that with migration to the newer technologies, you also have access to all the benefits that come with the newer technologies, which include faster processors that have the capability, greater capability, and more out-of-the-box functionality, such as safety processors that give you a platform in which you can meet the latest safety standards. More reliable and secure standardized communications with more access to remote access, easier management and maintenance. For example, you can use thin client HMIs instead of fat clients. Better integration across data and the likelihood of turning data into information. You can have less paper and fewer disparate data sources that are difficult to access. Looking at PLC scenarios, there are many legacy PLCs still in place. Allen Bradley PLC5s, Siemens TI-505s, and others. Spare parts for those are becoming more expensive and getting difficult to find. In the approach, we would do an assessment of the current installation and operational restraints. Looking at installation layouts, you'd want to find out, are all the I/O points wired to terminals? Are they going straight to the I/O racks? Are all the I/O racks in the same panel? Is the wiring in good condition? And are I/O points added and removed frequently from that panel? Looking at operational items, you need to find out how much downtime is possible to do your installation, and then what the requirements are for startup. For example, on an extrusion line, all of the items have to work pretty closely together at startup to get the system to function. Possible solutions for replacing the PLC, you can do one rack at a time. You could replace the processor, and then after that replace sections or racks of I/O. Advantages of doing it that way, you can do it in multiple short downtimes instead of a large single downtime. You have lower risk during the project because you can, if you do one of the installations and have an issue, you can revert back quickly to the original hardware. And disadvantages, it's more costly overall because you have more installation and startup. You could have more mobilization for your contractors and for your engineering staff. And then there's also the potential for confusion among your maintenance personnel during the installation because you have half of your system is with new technology and half of it's with old technology. You can do all the I/O simultaneously. Advantage of that is you'd have the lowest overall cost because there'd only be one mobilization, and then no maintenance confusion during the process. Disadvantages are it takes a longer downtime in order to change all your I/O at the same time, and you have a higher risk during startup. Reverting back to the original would take at least as long as the conversion. And then you can use some manufacturers have migration devices. Advantages of using those is it's very quick, and you have lower risk with wiring issues. Disadvantages are the hardware is costly, and then if the I/O is not connected to terminals and you add and remove I/O frequently, it makes that difficult. Looking at drives, there are also many legacy drives in place, such as Allen Bradley 1305s and 1336s. It's extremely difficult to get replacements, and the failure rates are very high now because the drives are old. During the approach, assessing the current installation, you need to look to see that there's enough space in the VFDs for the replacement. Look at the division of sub-panels in your panels, and check the old wiring to see what kind of condition it's in. Some possible solutions, if you develop a plan and have a plan in place to replace each drive as it fails, that's one approach. And the advantage of that is that it's inexpensive if you don't consider the downtime. The cons are that you do have unplanned downtime if you wait until it fails to replace it. And then if you want to upgrade your communication, say from remote I/O to Ethernet, doing it one at a time makes it more difficult. You can replace sub-panels of VFDs, build a new sub-panel, take the old sub-panel out and replace it. The advantages are it can be quick. You can test the new sub-panel in your shop and make sure that it's working well before you replace it. And you can, if you do drive in a big chunk like that, you can replace communications. So you can take them off of remote I/O and put them on Ethernet. Disadvantages are that the sub-panels have to be laid out in a well-divided way in order to make that work. If there's a lot of wiring between the sub-panels, then it makes it more difficult to do that. Another way is to replace groups of VFDs at one time. And you can do that in most panels no matter what how much wiring is going between sub-panels. And you can upgrade the communications doing it that way. The disadvantage is it'll take longer time, so you need longer downtime to replace big chunks of drives at the same time. For DCS systems, there are many DCS systems out there that are either no longer supported or are in the process of being phased out. Support for those systems is difficult to find as workers who supported those systems, either in-house or external, are beginning to retire. The approach during the assessment of the DCS system need to ensure that you have good as-built documentation available. Develop technology options for the migration along with pros and cons for each. And then once you select the technology to use, determine what the migration plan should be, whether you want to do a phased replacement or do a rip and replace. And for the possible solutions, in a phased replacement, you would replace part of the system at a time. Advantages are you have less downtime per installation, so you have multiple small downtimes. And then if you try to start up and have issues, it's easier to revert back to the original system. The cost can be spread out over multiple quarters or even multiple years on a large system. Disadvantages are it's more costly overall because you're doing small pieces at a time and then having to interface between new and old pieces. And then you also have to have that interface. So you have to have a custom interface between the new parts of the system and the old parts of the system, which has potential startup issues and also potential maintenance issues. For rip and replace, advantages are it's less costly for the entire project because you only do it at one time. And then there's no need for the temporary interface. Disadvantages are you need a long downtime to do it, and there's potential for longer startup period. And also for a large system, the cost, you're not going to be able to spread the cost out across multiple years. You do it all at the same time. For the DCS systems and for PLC systems, it's highly recommended that you do software testing and a software FAT before you start disassembling the system to do the installation. Okay, for HMIs, you can either have older hardware such as panel views that are not supported, or you can have old versions of software HMIs that are either not supported or they're not compatible with new versions of operating systems. In the approach, during the assessment, you should look for things such as how many operator stations are there for the HMI? What is the number of screens? Is there any scripting in the HMI? What networks is it looking at? Is it looking at old, difficult to support networks? And then look at the target controllers. Are there any obsolete PLCs that it's looking at that need to be taken into account during the installation? Possible solutions, you can use conversion tools for converting old HMIs to the new software, and that is quick if there's no scripting involved. A disadvantage is that if there is a lot of scripting involved, it may take you longer to do that and go back through all the old scripting to make sure it works than it would to start over. You could rewrite in a new version, and the advantage of that is if there is scripting, then you can detail out what you want the system to do and rewrite the HMI more quickly. And you can take advantage of the latest tools and features. Disadvantages are if there's no scripting in your HMI, then it's going to be more costly than using the conversion tools. Also, when you replace your HMIs, you can look at virtualization. If you use a virtual machines and thin client deployment, you can have less expensive hardware out on the floor. You can have easier control of your virtual machines, the operating systems, the software versions on the machine. And then if the thin client fails, it's easier for your maintenance people to go out and replace it. Okay, for networks, many industrial networks were started small and expanded as a flat network as more equipment was added. Facilities now have bandwidth issues and IP address conflicts, and some facilities are not even sure what is connected to their industrial network. So in the approach, you need when you analyze, you need to find out if the media is capable of the bandwidth that you're trying to put on it. Are there outside connections, either enterprise connections or internet connections to the industrial network? Are the switches maxed out? What is connected internally to the industrial network? And what devices are communicating with each other? In possible solutions, if you replace unmanaged switches with managed switches, it might help with some bandwidth issues, and that you can keep traffic, say multicast traffic, away from certain pieces of equipment. If you segment and route the network, then you can easily manage the bandwidth between segments, and you can control what can talk between the segments. And you can isolate rogue devices so that if someone plugs a rogue device up somewhere in your plant, it only affects a small portion of the network instead of a large portion. Additionally, with a segmented network, you can add DMZ and security from outside intrusion. All right, and I'm going to turn it back over to Richard to discuss obsolete MI.
Thank you, Tony. So MI is the category we're using to group everything from the automation layer up to the ERP layer, business systems like SAP and so forth. MI stands for Manufacturing Intelligence. Other folks refer to it as EMI, Enterprise Manufacturing Intelligence, Manufacturing Operations Management, MES. There's a lot of different flavors of that same area. So the typical scenarios that we run into for MI is systems running on obsolete software such as Windows XP or no longer supported software from automation providers. The Rockwells, Wonderwares, Siemens, and so forth who have discontinued their MI type of software. And then also custom-coded systems that are no longer supported. Our approach is the same approach that we would do for starting a project from scratch. We go through and develop a user requirement specification. So that focuses on who are all the stakeholders and users of this system going to be, what are their needs, what are the functions that they need to see, what type of reporting, and so on and so forth. From that, we develop the functional design specification, which describes the hardware, the software, and how the technical solution will be implemented to meet the user needs. We recommend a pilot system. So this would be a small version of the full-blown deployed project to allow the users to experience a test drive of the system, if you will. And then from that, we would collect learnings as to what tweaks the users may want. And then we do that before doing a phased implementation and then rolling it out, either rolling out multiple functionalities or rolling it out to multiple lines or multiple plants and so forth. There are many possible solutions in terms of technology platforms. There's different architectures, and all of these really are based and are selected based on the user requirements that are identified above. So in summary, many manufacturers now find themselves basically with a lot of obsolete assets, as we have described, obsolete automation assets. And there's risks associated with these when they fail. So this risk needs to be addressed in one manner or another. We recommend an obsolescence migration strategy that's basically going to be developed to describe the manufacturer's path as to how they want to go about addressing this. So part of that could be temporary patches like we described. The other part could be a roadmap to the desired future state. Could be a phased migration, rip and replace. But they need to have a plan as to how to address this obsolete hardware as it is no longer supported, as the parts fail, and so forth. The desired future state of automation really is the key opportunity in all of this because it's going to allow you to leverage latest technologies in a better way to meet present and future needs that are identified. So we described some of these latest technologies, but technologies from 10 to 20 years ago, as we're all accustomed to, with iPads and phones and everything else, obviously can't compare with what's available nowadays. And it's not about deploying the latest technology, it's really focusing on what are the technologies that are needed to help meet the customer's needs now, and then also the platform that they'll need to build for future needs that they see coming up. And then there's multiple options for implementation based on the risks, needs, available capital, and so forth. So we always like to talk about the business drivers, since business drivers typically are what drives funding for projects like this and helps justify the investments. One of the sustainable benefits is the ability to maintain a competitive market advantage with greater flexibility for new products and packaging to keep up with the speed of change in the market. So the more modern automation systems are going to be more capable to support these changes. So documentation is going to be better, support's going to be better, functionality is going to be better, and so forth. Higher operational efficiency for higher throughput, increased uptime, production flexibility, and reliability. We discussed most of that during the presentation. Lower maintenance costs due to decreased failure rate of newer assets, along with reduced time and cost for troubleshooting, reacting to having to replace parts. The upgraded technology also delivers an increased level of supplier support for the newer technology. And then the ability to better meet safety and regulatory compliance with all the new baked-in functions help ensure the plant will be able to meet these standards more easily. So with the obsolescence risk eliminated, a forward-thinking approach will enable production changes and expansions at lower risk and cost with automation hardware and software that's more reliable, better supported, provides increased functionality. So now I'll turn it over to Betsy for questions and answers.
Thank you, Richard and Tony, for this insightful discussion. Attendees, if you've not submitted your questions, please do that in the questions section at the bottom side viewer panel. And now we're going to address some questions that were received during the webinar. The first question is, for DCS systems, what do you see most folks migrating to?
Well, the current crop of PLCs, such as control logics, they have a lot of the power and abilities of the older DCS systems. And so we see a lot of people that are migrating from older DCS systems to things such as the control logics.
Great, thank you, Tony. The next question is, how does migrating your automation help meet safety standards?
Okay. The newer automation hardware, such as the guard logic PLCs that we talked about, redundant Cat3 devices, safe-off functions in drives, so forth, these are built-in safety features that make it easier to meet the latest machine safety standards. It's a lot easier to implement a machine safety initiative with this environment than with legacy controls where you may likely need additional hardware to provide this functionality. So, for example, a guard logic PLC allows you to program in the safety circuits, whereas with the legacy systems, you would have to hardwire these circuits to a new piece of hardware, like a safety relay that you'd have to purchase.
All right, thank you, Richard. The next question is, we're experiencing communication issues between assets, and it's beginning to impact our production performance. How would you begin to approach this issue?
Well, if you're having communication issues, would recommend doing an audit and assessment of the network, probably the entire network, because if you're having issues, it's probably not just one thing or one area. So you'd want to find out what the current network traffic is, find out if you're having cabling issues, having issues with switches, and analyze all those kind of things, and then make recommendations on how to remedy problems once you know what you actually have.
All right. We have another question. Is it now time for wireless on the factory floor?
Yeah, there are a lot of people that are using wireless. I would say that depends on several factors. If you're trying to use wireless to remote stations, then that definitely would be the case. If you're using it in the plant floor where it would be easy to use cables, maybe not. We've seen a lot of people using wireless stations to connect to the network for things like printers or barcode scanners and things like that. You need to check your wireless traffic and make sure you're in good shape to use it before you do that.
All right, we have no more questions. So in closing, I want to thank everyone for joining us today. We hope you found this webinar to be informative. A recorded copy of the webinar will be available on www.polytron.com next week. And when we close the webinar, a pop-up survey will appear on the screen, and we'd like to ask for your feedback. Again, thank you for attending.